Okay, hello, this is Dr. James, and today I'm going to do the reverse engineering of this nifty little RF induction circuit. It's got two transistor oscillator, and might be able to use this for some interesting projects if you understood the circuit, and maybe we'll make a spice model of it too, and test it out. And here I have the circuit diagram that I've been drawing out, and I'll show that in a second. So let's get started. Should be interesting. Okay, so I started the reverse engineering of this nifty device. This is a, I think I did a video on this a while back. This is a small version of the induction heater circuit. It's got a couple inductors here and a couple capacitors, some resistors, a couple transistors. And I started tracing out the circuit as I can see from the bottom. And I'm going to trace out the rest of it probably with a voltmeter. It's got some diodes, some resistors. I think the diodes are to protect the transistors. Looks like the transistors are a FET IRFP, International Rectifier 260N. They're rated for 200 volts and 50 amps. And I was going to measure some of the other components, like here's the inductor. Let's take a measure of the inductor. And I'm going to have to hold these on there because there's not really a good place to... Oh, I guess I can clip that one on. Okay. Okay, so that's about 101 microhenries. And the other one was about 90-something microhenries, so around 100 microhenries. So let me write that in here. 100 microhenries. And I'll try to measure the capacitors next. Let's see, the capacitors, I think. Okay, here's the capacitors. And they're from there to there. Okay. So I'll change this meter to from, see it's on inductance, I'll change it to capacitance. And we'll see if we can measure the capacitance of these capacitors. And I might make a spice circuit to just test this out to see if it behaves, you know, so I can model this and predict how it's going to react. I make some modifications to it. Okay, that's interesting. So around 20 microfarads. Okay. We'll say 20 microfarads. Okay. So this is going to be a nice high power device. I've been building some transistor oscillators, and this is exactly what I'm looking for, but I need to modify it a little bit because I want to be able to change the frequency of it. Anyway, there's a skew number of it, 009586, and it is the 2 capacitor type, which I believe are not too expensive. I want to say maybe around $20, but who knows, with the hyperinflation caused by you know, our this phony corona BS and our criminal leaders destroying our economy in the Marxist fashion that they are. Who knows how much these will cost in the future. Anyway, I'm going to trace this circuit a little bit more and fill this in, and then I will show you the whole circuit and maybe do a spice model of it. Should be interesting. Okay, so the next component I was going to look at is these pretty heavy-duty resistors here. And if you look at the circuit, it's claiming, I don't know if you can see that very well, it's claiming 470 ohms. There's some writing above it, but let's see if we can see that. Right in there, 470 ohms right above that resistor. 470 R means 470 ohms. But when I measure it, it's measuring a little bit lower, and I think it's because it must be in parallel with some diodes or something. In fact, when I measure it one way and measure it the other way, it seems to be different. See, I was trying to measure from the bottom. Maybe I can measure from the top. Maybe that would be easier. Pick some clip leads on either side of that resistor. Okay, 362 ohms. But if I reverse this, I'm pretty sure it's giving me something different. Hopefully I'm not going to burn out those diodes. Oh, I guess it's about the same. 360. Maybe it's in parallel with a transistor or a diode or another resistor or something. I'm going to, since they're claiming it's 470, I'm going to put it down as 470 and trace the circuit and try to figure out what the heck it's in parallel with, because I suspect it is in parallel with something. Okay. Very interesting, huh? Okay, so let's just take a look at the ratings of these capacitors, what they're supposed to be. And wow, so that's quite a bit different. It says it's supposed to be 0.3 microfarads. It's at 600 volts, 50 kilohertz, so they're high frequency capacitors. Anyway, it's very strange because it seemed like I was measuring something like 20. I'm not sure if these are in parallel. If they're in parallel, I'd measure, of course, you know, the parallel reading of these guys. If they're in series, I can measure them individually, but if they're in parallel, I'd have to break the circuit, which I'm not going to do right now, I don't think. Anyway, so I'm going to have to reconcile this. 0.3 microfarads, right? Huh. Okay, I'm going to have to look at this some more. Okay, so I'm pretty sure that I have those on the right leads for the capacitor, and now I'm measuring 48 microfarads. Maybe I can try reversing these and see what I get. Maybe there's a diode causing a problem here. Something. Okay, 48 microfarads, so I'm still very confused. Okay, so I put this on resistance here. Let's see. It's on resistance. And I'll just measure between the two terminals of the capacitor on this side. Okay. And it looks like... Oh, right, getting the leads on there good. Get them on there good. I'll try to get those on there good. Okay. 0.15 ohms, and that's what I get if I short them together. So it appears that these two capacitors are actually in parallel here. So I'll complete that circuit there, and we'll continue on and trace this circuit out. Should be very interesting, huh? Okay, so I have the clip leads hooked across the resistors, and it looks like I'm measuring about 460 ohms, and the resistors are claiming 470. See, there's a little thing there that says 470R, and so I think that's pretty close, so we can probably call that 470. Okay. Because they're supposed to be within 10%, right? Okay. And so I have one side hooked to the lower end of the resistor, and I think I figured out that we touch here. This resistor, the bottom side is connected to VCC, so the power is going through that. Let me check this one again. Okay. Okay, again, both of those resistors are connected to VCC. I suspect that might be some kind of pull-up resistor, because when you're making an oscillator, you need to pull the voltage of the gate up a little bit higher so that it will be close to the switching place, so you can get it to oscillate better. And so that's what I suspect these resistors might be. Okay, let me add that to our circuit down here. Okay, so I have the clip lead hooked onto the one side, the top side of the resistor now, and I suspect that that hooks to the gate of this transistor. I just wanted to check that. It looks like the resistance is very low, so I'm going to draw that in. So this is a pull-up resistor. Those big resistors on the back side, these ones right here, are pull-up resistors, and looks like they pull the voltage up on the gate to get it at a high level, so it'll have be close to the switching point, so it'll be easy to get it to, or possible to get it to oscillate. Okay, so I'm going to write those in. Okay, so these are the small resistors that are across these nodes right here. So let's test to see what they are. Let me get a good connection on that. Okay, so about 5.2K. I should be able to look at the coloring on it as well. It's hard for me to see that though. So that K should be a red stripe for the third position. It's really hard for me to see that color. Let's see, it goes brown, black, red, orange, yellow, green, blue, violet, right? There's, this must be a high precision resistor because it's got extra stripes. Okay. So I would have expected brown is 0, black is 1, red is 2, orange is 3, yellow or white. I don't know, I'd have to look at that some. Doesn't seem like a 5K, but maybe it is. Okay. Okay, so in this circuit there seems to be pairs of a resistor and a diode. Let's take a look. Resistor and diode that are coupled together right here, and it looks like they are probably tied together on the other side from my ohmic measurements. So these two are tied together like so, and it seems like they go from the ground here to the gate. Okay, so that is to discharge the gate using a resistor. So here's the gate of our transistor on this side, and it seems it connects to these diodes to discharge them. Okay. Like so. And I suspect this circuit is symmetric, so that these ones here should go to the gate on the other side as well. So I suspect, I'm going to test that, I think these ones should go to the gate on the other side. Okay, so I think we're making progress with this circuit. Okay, so I think I drew that incorrectly a second ago. I drew that one over to this one, but actually these diodes come from the ground and they go over to the gate of that one. So we have VCC going to both of these big resistors, which is going to pull the gate up into the middle, and then it's going to have these diode and resistor combination. Well, the resistor is going to pull it down, and I think the diode is going to help it discharge in a certain direction. And so these are connected to ground, so it goes from VCC through this resistor, connected to gate, which is going to bias the gate at a certain level. And then this is connected to ground, so this is like a resistive divider between the 470 ohms and the 2.5K. Okay, and I suspect these are to discharge the diode in a certain direction. So when it's oscillating, and there's a couple more diodes up here, and I'll have to see where those connect to. Okay. Okay, so here's the gate of that transistor, and here's that big diode. And when I hook those up together, we get no impedance between those 2 points. So it appears these 2 top diodes here act as feedback. They connect the gate, the drain of one side, which is, see, the drain here of our circuit is connected to this resonant circuit, and so it's going to oscillate up and down as this circuit resonates. And this drain is actually connected through this diode to the gate of the other transistor. So when this gate drain switches up and down and this circuit oscillates, it's going to provide feedback into the gate, and vice versa. The drain of this one's hooked up to this other diode, which provides feedback to this gate. So let's take a look here at what I'm talking about. So these are the big diodes up at the top. So this diode here provides a path from the drain of one side to the gate of the other, and the other diode does the opposite, drain of this one to the gate of the other one. Okay, so these 2 top diodes provide the feedback to allow this device to oscillate. Very cool, huh? Okay. Okay, so I think this might be our complete circuit here. And there we go. Let's take a look here. So let's go through this one more time. We have VCC and ground, and VCC powers the inductors, and then it will go through the drain source to ground. So these will switch on and off, putting voltage across the inductors. And then there's a resonant circuit created by these inductors here, which is partially coupled. It's asymmetrical. See, it goes from one capacitor to one inductor, so this circuit is asymmetrical on the output here, which is interesting. So you can put another inductive load out here and it will tune this a little bit, this resonator here. Okay. And then we have feedback from the diodes. Since the drains are connected to this resonator, they're going to have feedback, well, I guess the resonator will feedback directly into this diode and drive the gate. One will drive the gate of one transistor, one will drive the gate of the other, depending on the polarity, it looks like. And then we have some we have a second circuit. We have to bias the gate upwards, or else it won't turn on. Alright, so it's got to be biased high at some point. So we have VCC going through the 470 ohm resistor, which forms a resistor divider with the smaller 5.2k ohm to ground, and the gate's in the middle of that, so that biases the gate up high. But we have a diode here to help drain the gate, I believe, during the oscillations, help it switch off quickly. Okay, and again, these FETs are International Rectifier IRFP260N, rated for 200 volts and 50 amps, although I wouldn't probably put 200 volts on this because some of these other components may not be rated for that, and they may not like it. I think this device is rated for like 48 volts or 24 volts or something like that. So probably better stick to the design of that. And, okay, anyway, very cool, huh? There's the reverse engineering of our RF induction circuit. And we'll be able to use this for really high power oscillators. Very cool, huh? Okay, so here's the spec sheet of the IRFP260, and it is a field effect transistor with a diode in there. And here's some of the specs. 200 volts, 50 amps. Very cool, huh? Very nice transistor. Very high power transistor. Okay. Let's see. Let's see if it says how many watts, but you should be able to figure that out, how much power it can switch. In principle, 200 volts times 50 amps is 10,000 watts, is that right? 2 times 5 is 10, and then there's 3 zeros, 10,000 watts capable of switching. Wow. Very cool. Okay, so here's our device, and they're rating it at 1,000 watts. And looks like it sells for a little bit less than $50. I think it was cheaper than that before, but everything's going up in price with the dollar collapsing, right? It's a phony pandemic. Well, we'll see. Should be interesting. I think we can have some fun with this device, though. Let me begin with reverse engineering it. Very cool, huh? Okay, so here's what I think the circuit looks like for this guy here. Okay, I don't know if he's coming through very clear, but anyway, I had to use a different transistor because I couldn't find the exact same one in the parts list. And I tried to get this to oscillate, and it doesn't seem to be oscillating, so I'm going to fiddle around with this, but I'm pretty confident that this is the correct circuit here. And it's drawn out a little bit nicer here on the schematic. Okay, so let me fiddle with this and see if I can get it to oscillate. Okay, so the circuit's not oscillating, and I just wanted to check the resonance frequency. And as I suspected, the resonant frequency is very low. That's in megahertz, so that'd be 1.6 kilohertz. And I think it oscillates much faster than that. I have to check back, but I think it was in the tens of kilohertz. And so I suspect maybe because the capacitors are inside of the circuit, and it has resistors and other things, and our LC circuit measuring device probably makes some assumptions about the, puts a resistance in there and charges it up, and so if there's other resistors coupled to that capacitor, it may interfere with the measurement of the capacitance, and possibly even the inductance. So, remember, we did see a different capacitance value on the capacitor, so maybe I'll try that one and see what that gives us. Okay, so excuse me. Okay, so I put the value of the capacitance that is stated on the capacitor times 2 because they're in parallel, so that's about 0.6 microfarads. And that's given us a frequency, I think, closer to what we were seeing before, 14 kilohertz. Okay, assuming that the measurement of the inductances are correct, which I think they probably are. So let's try that in our circuit model and see if that helps. Okay, so I found this article on the web, Understanding Royer Oscillator. This is under Stack Exchange, and I'll probably include that link. And this circuit looks pretty similar to what I was guessing our circuit looks like, except for it looks like they have an extra capacitor. It's very similar. They have the diodes here and some biasing resistors, feedback. It's a little bit different, I think, unless I got the circuit wrong from tracing it. But let me compare this to what we have and see if we can figure out why this thing is not oscillating. Okay, so here's another Royer oscillator circuit, and it looks almost identical, having the single capacitor in the 2 inductors being fed in the center. Actually, it's got a third inductor there, but it's got the resistor divider here to hold the gate voltage up, and diodes on the gate doing feedback from the resonator circuit. Okay, so it looks very similar to the circuit that we have. So except for our circuit had some extra diodes in it. But I'll take a look at this and see if we can figure out why the thing is not oscillating. Okay. Okay, so I was looking at trying to figure out why this circuit wouldn't oscillate, and of course these are different transistors, and so I was looking at the gate input, and it was biased way too high, so it was never shutting off the gate. So I increased the value of these resistors, which were, I believe, 5.2K from what I measured. I decreased them down to about 50 ohms, so it would see, we have the voltage divider 470 to 50, so it would bring the voltage down on the gate closer to switching off, and I still wasn't able to get it to oscillate, so I let's see if I can get into this guy. Okay, so here's our signal generator, and I'm putting in 50 volts DC, but I'm also putting a tiny little 0.1 volt ripple at the resonant frequency, and to get the oscillator started. And I really shouldn't have to do that, but I was able to get it to finally work by doing that. Okay, so we simulate it, and we'll just look at the current going through our output capacitor. And actually I was looking at the circuit, and the output is actually across this capacitor if you look at our circuit here, because even though it looks a little bit asymmetric, it's not. This is one side of the output, and the other side comes from the other side of the capacitor. So the output is basically across the capacitor, like so. And so you can see that it starts out with low signal, and then the oscillations take off. And let's take a look at the gate input, because remember I said the gate. Okay, so now the gate is switching good. Before it was like the bias offset was way high on the gate, so we're getting strong switching in the gates, and okay, getting high current through our inductors. Okay. And the oscillation voltage is pretty high. It's about 50 volts. So it looks like, actually it's not that high, is it? But it is, I think it is oscillating by itself. I'll have to fiddle around with this circuit some more, but I suspect it has to do with the bias resistors on these guys not being correct for this transistor. And since this is a different transistor, or it could be I'm just using generic diodes. Maybe these diodes don't have the same properties or something, but I believe the circuit is pretty much correct, because it's pretty similar to the circuit that we're looking on the internet there with the Royce circuit oscillator. Okay, and again, I'm only putting in a tickle of like 0.1 volts, and it's got a pretty big oscillation for that. So I think it wants to oscillate. It's just the conditions are close but not exactly right. I said add a little seed oscillation, it amplifies it. Okay, so maybe I'll fiddle around with this some more, but if I don't find anything better, then I think we'll have to end this video, and we'll do something else in the future with this. Try tuning this guy and see if we can use it for some other projects. Okay, so I guess setting the bias resistors to 50 ohms was too low, because I set it to 100 ohms, and now I'm getting a lot higher power output out of the oscillator. And better switching at the gate. Okay, again, this is the voltage output and the current. Okay, so let me just try, maybe I'll go to 200 ohms. So these values, I guess, have to be set just right for the particular resistor to get your oscillations. Okay. Simulate, run. Very interesting, huh? Maybe I'll set the bias See if I can set the bias to 0 and still get it to oscillate. Remember, I'm tickling it with a little bit of ripple there to get it to go. No, still not. Okay. But it's close to oscillation because it amplifies those tiny little ripples into a strong oscillation. Okay. It's just not starting up on its own. I'll put this ripple back in. That's only 0.1 volt out of 50. So that's a very small ripple. And it definitely puts out a huge amount of voltage oscillations with that small amount of ripple. Okay. So I believe this is the proper circuit, pending the resistance measurements, but we should be able to do something with this end here because this determines the oscillation frequency, and we should be able to change that to modify our frequency that it puts out here. Anyway, hope this is helpful to you. We'll do some more stuff with this circuit in the future. Okay, so I think I was finally able to get it to oscillate, and what I did is I changed the power supply here to a step function, so it starts at 0 and then it ramps up to 50 volts in 1/10 of a millisecond, and then it stays on for a long time compared to that, 100 milliseconds. And let's take a look here. So this is the current through this inductor down here, and it looks like it's oscillating. Steady state, looks like it starts up. So you need some kind of transient, I guess, to get this oscillator started. Some of the others are absolutely unstable, so let's take a look at the FFT here. Okay. And okay, looks like our main peak is around here, which is around, that's a little bit higher than what I calculated, so it's about 15.5 kilohertz. Okay, it looks like it's self-oscillating now at that frequency, and again, I believe the how well it oscillates depends on the resistors that you choose here. Move this back. So, okay, so very interesting. I'll be able to look at this circuit a little bit more. And okay, so there's the current going into the FET, so it looks like it's switching, or the voltage going into the FET, the gate. So it looks like it's switching pretty good. And there's the other gate. So it's definitely driving an unstable oscillation. I don't know why it's not balanced though. Maybe it is. I see. This one just has a big transient at the front, so the current doesn't look that big. But it's still 10 amps. This one doesn't have the big transient, so it scales up. Okay. 10, 15 amps peak to peak. Okay, very cool. Finally got this circuit to oscillate. Okay. And so I believe this is the correct circuit, pending, minus that I had to use a different type of transistor, so I had to bias it differently with these resistors here. But it looks like it's a good circuit to oscillate, used for high power oscillations, high power RF generation. Anyway, very cool, huh? Okay, so I got the 18650 battery pack with 4 of them in there, because this device says it works on 12 to 30 volts. See if I can get that in the focus, maybe not. Anyway, 12 to 30 volts. Okay. And I'm just hooking up one side of this because I'm afraid this resonant circuit might go to a very high frequency. Just hooking up one side of my scope probes here. Okay. So then the other side is just capacitively coupled, so it won't get the full voltage across the probe, and hopefully won't burn it out. And I got it hooked to my oscilloscope over here. And I like to use that one because it's easier to measure frequency, because I wanted to see what frequency that this thing is operating at. Okay. And let's see, I'll get the cursors down here. Doesn't look like a very resonant frequency to me. But, okay, very interesting. So without a coil on there, it kind of does some kind of weird oscillations at a very low frequency. Okay. So maybe I'll hook up a resonant coil to it, and we will see how this thing operates. Okay, it's been wanting to go into the low frequency mode even when I put this inductor on it. But it looks like I got it to oscillate in a high frequency mode. Let me measure the frequency of that. I'm not going to run it too long because I don't want to destroy my batteries. See, the low frequency mode sounds like this. And it's mostly going into that mode, but I did get it into that high frequency ringing mode. And let's see, so that's about 10 kilohertz, which is about not too far from where we predicted without the coil in there. Remember, we were predicting about 15 kilohertz resonant frequency of this guy, but it does not seem to be resonating nicely most of the time for some reason. It's starting up in a weird oscillation mode that's low buzzing type of thing. So anyway, but it looks like I did get it to oscillate at the higher frequency mode. Maybe it's designed to operate with lower inductance coils more. Let me put a lower inductance coil on it, and we'll see how that operates. Okay, so I hooked up a smaller high inductance coil on the output, which, remember, when I was doing the reverse engineering of this guy, is just in parallel with these two capacitors here. And I have a scope measurement here now of that frequency, which is around 116 kilohertz. Okay. And maybe I'll fiddle with this. Maybe I'll try putting some inductors or ferrite cores in the middle of that and see if we can change the frequency. Anyway, this is Dr. Janes, and thanks for watching.